So we'll start. Last time we introduced Dirichlet L functions. So last time we introduced Dirichlet's L functions, L as chi, so these are, well, we take a character mod q defined on the coprime residue classes, and we define the L function simply by setting Dirichlet series like so, simply by setting chi of n to be chi of the residue class of n mod q. If n is not coprime to q, chi of n is just set to be 0. And so this we noticed because of periodicity and boundedness of the partial sums that actually it converges for real part of S bigger than 0 if chi is not the trivial character being denoted by chi 0. We use this to notice, we use these to deduce that if I take the combination summation chi bar of A minus L prime of S chi over L S chi, if I take this combination and sum over the characters chi mod q, so when I write this I'm talking about the characters, the character group of this thing, and when I divide by phi of q, we got that this is equal to summation n less than x lambda of n congruent to A mod q. This is what we got last time. So on the right hand side we have essentially primes in the progression A mod q. On the left hand side we have this concoction of analytic objects. We would like to deduce something about the behavior of this, sorry, this is n to the s, thank you. Right. And now I'd like to apply the Tauberian theorem, right, to deduce something about the partial sums. Sorry, this should be n. There. Is that okay? Yeah. It's a Dirichlet series, and I'm getting ahead of myself. I'd like to now deduce, we can apply the Tauberian theorem to deduce what? Deduce something about the partial sums. So the Tauberian theorem tells me if you have a Dirichlet series with non-negative coefficients, or even, it doesn't matter, complex coefficients, we went through that discussion with some suitable properties that this Dirichlet series now is the same as this Dirichlet series. From this Dirichlet series we deduce that this has analytic continuation for real part of S greater than or equal to 1 with a simple pole at S equals 1 with residue 1 over phi of q, except we need to know that these guys don't vanish on the line real part S equals 1. Okay? So we can apply the Tauberian theorem to deduce this as x tends to infinity, provided the Dirichlet L function is not 0 for all chi for real part s equal to 1. So we need this. We need the non-vanish. So we know that for chi equal to chi naught, that's really the zeta function. That we know, we've already proved that it has no zeros on real s equals 1. But now we need to prove that for the other characters, there are no zeros on the line real s equals 1. That's what we need to prove. So this is the critical part of the proof. Somehow a theorem of this type about primes in arithmetic progression translates itself to some sort of non-vanishing of an L function. And that's so this kind of symmetry between non-vanishings of L functions and asymptotic statements are common in number theory. So this is what we need to discuss today. Everybody okay that this is essentially the prime number theorem in arithmetic progressions? Because the contribution from squares, cubes, and etc. is small. And so the main thing is really coming from the primes and not prime powers. Everybody okay with that? Yeah, okay. All right, so now this non-vanishing result, as I mentioned last time, Dirichlet had a tough time doing that. 1837, he took a couple of years onwards and did it really in a very complicated way. Of course, as I mentioned many times, it's not necessarily the result that we're after, but rather the proof. We're trying to look for methods. So Dirichlet's efforts in trying to show that these L functions didn't vanish, of course, he was not after the asymptotic formula, he was only after the infinitude. And for that, you don't need all this tight information. It suffices to know L1 chi is not 0, because he was only showing a very weak statement. He was basically showing the divergence of a certain series. Okay, so the easiest way of handling this problem is using what's called Landau's lemma. A very important lemma in mathematics, in number theory in particular, and it goes as follows. If a sub n's are non-negative numbers and the Dirichlet series f of s converges absolutely, so maybe I shouldn't say if, I should say suppose that the a sub n's are non-negative numbers, and that this Dirichlet series converges absolutely for real part s bigger than sigma naught. If f of s admits an analytic continuation to real part s bigger than or equal to sigma naught, analytic continuation completely, no poles, i.e. no singularities, no poles, then the Dirichlet series converges then then there exists an epsilon positive so that the Dirichlet series converges for real part S bigger than or equal to sigma naught minus epsilon. So this is it's a theorem really in complex analysis. So it's a statement saying that if I have a Dirichlet series which converges absolutely for this region, and supposing this has an analytic continuation to a larger region, then the Dirichlet series itself actually converges in this larger region and is that function. So it's a kind of very interesting statement being made here. So let's see how we prove this. It's pure complex analysis. So prove well by shifting with we're shifting the redefining A sub n if necessary, we can assume sigma naught is 0. So without loss of generality, we may suppose sigma naught equals 0, because you could just replace an by an over sigma naught. Shift the whole business to that. Okay. So having done so, then the hypothesis of the theorem tells me that the Dirichlet series converges for real part as bigger than 0. It has an analytic continuation to real part as equal to 0. And then the Dirichlet series actually converges at 0 and even to the left. That's basically what this is saying. And so let's see how that works. If the function admits an analytic continuation to 0, then there's some small neighborhood of 0 for which it's analytic in that region. So here's S equals 1. Let's just keep. And so that means I can draw some circle. Oops. I'm bad at drawing, so. So here's the circle in which the thing is analytic, okay? So I'm going to draw the circle in such a way, centered at 1, in such a way that this, okay, this is not a circle, wait a minute, sorry. Sad thing is that this is even being filmed, so. So let me draw a circle first. Does that look like a circle? Okay, good. That looks reasonably like a circle. I want to have a circle centered at 1, and I want the region that extends to the left of real part S equals 0, so this is real S equals 0, to be that little bit that it extends to should be in that neighborhood in which the function is analytic. Okay, so now I know that in this region, firstly there exists an epsilon positive. This is all I want to say, such that for this region, f of S is analytic in this region. So there exists an epsilon positive such that for all S in this, sorry, yeah, I want to put 1 plus epsilon. Thank you. Yeah? So, yeah, this little itsy bitsy bit here. Epsilon should be small, so you don't want to make it bigger than 1. This is part of mathematical theology, I guess. So, anyway, okay, so f of S is analytic in this region. And so it has a Laurent expansion. Okay, so it has a f of S can be expanded as a Laurent series about 1. Okay, Taylor series, or in complex analysis, it'll be called Laurent series. Now, what is Fk of n? So here, now I'm in the region of absolute convergence. Remember, the Dirichlet series converges absolutely for real part s bigger than 0. So 1 is certainly in a reasonably good region. The Dirichlet series converges absolutely. And so you have f of s in that region given by an over n to the s, right? That's the Dirichlet series. And so if I want to differentiate umpteen times I differentiated umpteen times and get, right? And so if I was to put s equals 1 now, which I can, this is an absolutely convergent series, right? So you get that. And so I'm going to use this expression and shove it. This Laurent expansion converges absolutely in this disk, okay, and the region of analyticity. So let me now rub this bad picture off. We'll continue here. So now plug this back in here. Everything is now convergent absolutely. So the minus 1 to the k, I'm going to put 1 minus s to the k. Everything is convergent absolutely. Okay, but that's why I moved to 1. It's a safe place. And now, so I interchange summation and recognize that the inside sum is the sequence for e to the power 1 minus s log n, which is basically n to the power 1 minus s. This is all valid in that region. So now choose s equal to minus epsilon, which you can do because I took away that picture, but remember that picture was something. Maybe this is the way I should have drawn it first. and then made a little thing like that. But anyway, okay. So there's a little bit of an epsilon that goes out there. So I choose that, which is valid because I'm still sitting inside this region. When I do that, you can see that it becomes 1 to 1 plus epsilon, and therefore this actually still converges, and therefore you get an n to the epsilon converges, which is the Dirichlet series at minus epsilon. That's the proof. Okay? That's the proof of Landau's theorem. So it's a very interesting theorem. It's a theorem in complex analysis and relatively easy to understand if you have some basic intro to that. Okay? So the region of analyticity. So there's this very powerful tool, actually, this thing is. And now we're going to use it to show non-vanishing. Everybody okay with that? All right. Okay, so I'm going to rub this off if everybody's finished copying. Okay, well, okay, I'll rub this off then. So we want to apply this theorem. Now, so we want to apply this, Landau's theorem to show LS chi is not 0 for all chi real part s equal to 1. Now, you will recall how we did this for the Riemann zeta function. We used that trigonometric identity, 3 plus 4 cos theta plus cos 2 theta non-negative, right? And you might think at first hand that how come we can't use that trick again for this situation? And actually you can. You can. You'll see that you can do that. You can get away with it, except there's going to be one point where you can't use that trick. And so at that point I have to use Landau's theorem, okay? So let's see how that works. So we want to prove the non-vanishing, so here's how you kind of do it. So you kind of consider product LS chi. So let's call this guy f of s. Okay. And remember, each of these LS chi's is another Euler product. And so if you think about it, let's see, the easiest way to do this is probably right? I mean, I have an Euler product, and I do that, right? Now, this guy, the inside guy, I can write it as, so if I write, I mean, I can rewrite this guy here as exponential summation chi minus log 1 minus chi of p over p to the s. Okay? You may wonder why, but you'll see in a second. I can write this product as this thing. Exponential of log is the inverse function, so you can do that. And now that allows me to write this as exponential. So remember, minus log of 1 minus x is summation x to the n over n, the usual expansion. So this is an expansion over all n. So firstly it's over chi, and then over n, chi of p to the n. Now remember, it's a completely multiplicative function, so let's put it in here. Everybody okay with that? Okay, now you know, remember the orthogonality relation, summation chi of A is equal to phi of q if A is congruent to 1 mod q and 0 otherwise, right? Got this orthogonality relation. So therefore, if I shove this summation here, this whole product here turns out to be product over primes p exponential of phi of q summation 1 over n p to the ns p to the n congruent to 1 mod q. Everybody okay with this? Now what's the advantage of doing this? The advantage is this is a Dirichlet series now with non-negative coefficients. The problem with the characters was it could take on roots of unity, it could go all over the place. But considering this neat combination allowed me to make a Dirichlet series with non-negative coefficients. Therefore, f of s has got to be a Dirichlet series with non-negative coefficients. It's just the product of the whole thing, right? This implies that f of s is a Dirichlet series with non-negative coefficients. Okay? So, in other words, and now this is probably a good thing to understand with respect to the role of abstraction. I mean, the idea of that 3 plus 4 cos theta plus cos 2 theta non-negative trick really has nothing to do with the Riemann zeta function at all. So we're basically writing, so we have a situation where we are writing f of s as exponential g of s, where g of s is a Dirichlet series b sub n over n to the s, with b sub n's non-negative, right? I mean, we have such a situation like this. Therefore, like if I look at this combination, I write this as summation. I write this as exponential of, well, it'll just be bn over n to the sigma okay, I'm going to now take absolute values. Remember, with the same old absolute values, so the log of z is equal to log of the absolute value of z plus I times the argument, right? So if I take that, then you'll see that this is really 3 plus 4 cos t log n plus cos 2t log n. So that's what that is. Do you everyone see this? Because that's exactly what we did in the Riemann zeta case. In the Riemann zeta case, we also had that when we take the absolute value of this complex number. What am I saying here? I'm basically saying that e to the, let's see, z can be written as well, essentially r e to the I theta as a complement. So mod z, of course, is equal to sorry. Can I just leave this as an exercise, or do you want me to? So what's going on here is you have this 3 times g of sigma plus 4 times g of sigma plus it plus dot dot dot, and what we're doing is when you take that, remember essentially you're taking the real parts of the of this combination. So when you, if I were to have put this thing in here, it would have been 3 n to this it, well, 4 over n to the it, and so I'm just taking the real parts, and this is what you end up getting. Okay, so now this is non-negative, therefore the whole point is that this is bigger than or equal to 1. Okay, and we now suppose, let's suppose t is not 0 first. Suppose t is not 0, and suppose that if f of 1 plus it equals 0, then what happens? Well, remember that one of these things is the Riemann zeta function at chi equal to chi naught, and that's got a simple pole. So therefore, f of s has a simple pole at sigma equals 1. Therefore, there's a pole of order 3 here. And if it happens that f has a 0 at 1 plus it, that'll introduce a 0 of order 4 at sigma equals 1. Okay? And that would cancel that pole and make the 0 dominate. And then this guy's analytic, and therefore, as limit sigma tends to 1, the left-hand side should tend to 0. But it shouldn't, because it's at least 1. Okay? So this argument, the argument that was used to show the Riemann zeta function doesn't vanish on the line real part s equals 1, actually works for LS chi's also, because none of these things will vanish provided you use this function instead of the zeta function, and the argument more or less runs along this line. Everybody okay with that? Now, why did I have to assume t naught equal to 0? Why did I have to assume t naught equal to 0? In this proof. Actually, this proof works, doesn't it? If t equals 0, then, and I guess if t equals 0, there's a part of a problem, right? Because then I'm looking at, yeah, exactly. If t equals 0, I'm looking at f at 1, right? And that's got a pole again. Okay. So if t equals 0, this argument doesn't work. This argument doesn't work because there's still a pole there. So if t equals 0, I've got a pole of order 4, a pole of order 3, you know, and so this whole thing's got a pole at sigma equals, there's nothing, no contradiction. Sigma goes, it explodes, all right? So this started because the limit process doesn't work, because f of s has a pole at s equals. So if I was dealing with, if I wanted to show f of f doesn't vanish for any other t which is not 0, this argument works. So that argument for the Riemann zeta function case actually nicely translates to do this except at 1, except at s equals 1. So this argument fails. And this is actually at the heart of why Dirichlet had trouble. Is this small thing, you know? So sometimes when we get into these snags, we're irritated, but that there's an obstruction. But maybe you're putting your finger on something extremely important. And he was. So let's try and see how to deal with t equals 0. Well, if you, in that case, if L1 chi, you want to show L1 chi is not 0. Okay, so if L1 chi were 0, then what happens in this product? In this product, the pole at s equals 1 coming from the trivial character is eliminated by the 0 from L1 chi. So, okay, if L1 chi equals 0, then f of s is analytic for real part s greater than or equal to 1. The pole got eliminated, right? Before we knew that this thing was analytic for real part of s strictly bigger than 1, and at s equals 1 it had a simple pole, we said. but it's now viewing zeta as a factor there, possible simple pole. So now if the pole got eliminated by a 0, then the thing is analytic for real part s greater than 1, okay? Now, Landau's theorem is applicable, right? This is a Dirichlet series with non-negative coefficients from this concoction. Non-negative coefficients is analytic for real part s bigger than or equal to 1. Therefore, what? Therefore, it extends. Now, f of s, thus, we showed, remember we showed the Riemann zeta function has an analytic continuation for real part s bigger than 0. And we showed that all these LS chi's were analytic for real part s bigger than 0. The pole got cancelled. Now, therefore, this function is analytic for real part s bigger than 0. Thus, f of s extends to an analytic function for real part s bigger than 0. Okay, but let's just see what's going on here. Let's see what's going on here. So that means, in particular, this Dirichlet series should converge for any number with real part s bigger than 0. By Landau's theorem, right? Landau's theorem says if you have an analytic continuation for real part s bigger than 0, the Dirichlet series actually converges there now. So therefore, this Dirichlet series has to converge for any point for real part s bigger. In particular, it should converge for s equals 1 over phi of q, which seems to be a positive number. Okay. Now, notice that every prime satisfies this congruence with n equals phi of q. That's Euler's theorem. See, Euler's theorem tells you that p to the power phi of q is always congruent to 1 mod q, right? That's Euler's little, right? So that means every prime is going to appear here. Yeah, so every prime and phi of q. So now what happens when I plug in s equals phi of q is that I'm going to get a 1 over p as a contribution. Okay, n is equal to phi of q. S is equal to 1 over phi of q. And there's going to be summation 1 over p, but the sum of the reciprocals of the primes, remember, diverges. And therefore, it can't converge because otherwise, right? We kind of saw that from earlier work. Therefore, this actually diverges. So at this point, this series diverges. So that's the proof that L1 chi is not 0. So the point at s equals 1 is actually a very subtle point to analyze. And it requires a little bit more care. How did Dirichlet circumvent this problem? He actually calculated L1 chi explicitly. I mean, he did realize that there were, here's how he did it actually. He realized that if chi was a complex character, okay, if chi was and L1 chi was 0, then L1 chi bar is also going to be 0. So you'll introduce a double order 0, but this guy at chi equals chi naught has only a simple pole. Therefore, this argument actually still continues to work in that case. That the poles, there's too much of a 0 if chi was not a real character. So the only problem arises for chi is a real character. And when chi is a real character, Dirichlet went about going and calculating what L1 chi is. He related it to the class number of imaginary or real quadratic fields, and then showed that it's related to the order of a certain group, and therefore it can't be 0. That's how he went about doing it. Very, very complicated way of getting it. But now, of course, that formula is very important. It's called the class number formula. It's very important. Okay, so that's the proof of the infinitude of prime. Well, not infinitude, but we actually have the Tauberian theorem giving you asymptotic formulas. All right. Okay, so let me make a few general remarks. So we've proved the following. You take psi x q a if this is the definition, then psi xqa is asymptotic to x over 5q. Of course, a and q are always relatively prime. So that's what we proved. So the obvious question that one can ask is, what about the error terms? How does it go? How does it go to this quantity as x? So what about error terms? So if we let E x q be the maximum a q 1 let this be that, then what's called the generalized Riemann hypothesis, namely all the zeros of the L functions are always on the line real part s equals a half. That's the generalized Riemann hypothesis, is equivalent to the statement that EXQ is O of x to the half log QX. That right? Let's see. Maybe I better throw in a square there somewhere, yeah, to be on the safe side. You know, let me put log x log qx. There's only for the connoisseur is this distinction very important, but anyway. Okay, so that's the theorem. The q is not in the both of the logarithms. The Riemann hypothesis is equivalent to that. Unconditionally, if you fix q, you could make some statements about the error, but there are all these problems called problems with a real zero coming from, again, that real character, that nasty real character, and that makes these error terms not so neat and clean. So I don't want to get into the discussion of here, but let me just point out there's a famous theorem of Bombiri and Vinogradov. Which tells you that if you take the EXQ and you add this up up to x to the half over some huge power of logarithm, then this is less than x over so basically for any a positive, there exists a b, which is a b of a, such that this thing holds. Now, what is the great thing about this? Well, the great thing about this is this is an unconditional theorem, personally. And if I had the Riemann hypothesis, each of these terms would be like root x. Each of these would be like root x, that's what it's saying. And then I'd add up all these terms. How many terms are there? About root x. So I'm getting x over a power of log. So I'm getting an error term, which I would get if I had the Riemann hypothesis. So this is an unconditional theorem. And this, the fact that it's unconditional means that you can apply this to lots of cases where you need the Riemann hypothesis, but you don't need to assume the Riemann hypothesis. So this is often a substitute for GRH in many problems. Some of you are, maybe will be attending my lectures on new directions in sieve theory, where I'll talk about bounded gaps. This is one of the key ingredients in that theorem of bounded gaps between primes. So this is not a this does actually, it's an interesting topic in itself, but you need the large sieve to prove this. Okay, and as I said, error terms. If you want to do error terms, you need to have at least different techniques. So the Tauberian theorem is too general, and it doesn't provide error terms. Although there have been people who have researched into trying to deduce error terms from the Tauberian theorem. They're not very good error terms, but people have done this. But perhaps it's basically of theoretical interest. They're not very good error terms because in such generality you can't expect to get such good error terms. So there are two types of ways of getting error terms. One is the method of counterintegration. And the second method is elementary methods. I mean, as I told you, elementary doesn't mean easy, okay? Elementary methods. So let me say a few words about these two aspects. Let me talk about the method of counterintegration. A key point is that you use what's called Heron's formula. Which is the following. If you take this vertical line integral, so here you are in the complex plane, and I'm just integrating it from minus infinity to infinity. Instead of from minus infinity to infinity in the real world, you kind of integrate it along the vertical line. This particular function, and the idea is that this is equal to 1 if x is bigger than 1, 1/2 if x equals 1, and 0 if x is less than 1. So it's a simple exercise in counterintegration. So what you do is there's a singularity here. I'll leave this as an exercise. Singularity at s equals 0. So it's like a line integral. Heron discovered this. Now what's so great about this? Well, here's the reason. If I have a Dirichlet series, like so, and I really want to get asymptotics for this, which is what we were trying to do before, well, there's a nice way to write that, and that is where, of course, we should take the following understanding. So notice that this thing, if the Dirichlet series, let's say, converges absolutely for real part of S bigger than 1, so I'm in the region here, I'm real S equals 2, therefore this thing converges absolutely. I can interchange the integration and the summation, and you can see now that this is going to be summation A sub n times this Heron integral x over n, which is going to spit out a 1 when x over n is bigger than 1, which is exactly the range I need it in. That means n is less than x. And it'll spit out a half when x equals 1. That's why I put the star there. So when x is an integer, it's not going to pick out an, it's going to pick out an over 2. So it's a small, but that's a minor issue. So here I've expressed the sum that I'm interested in as some sort of complex line integral, which is 1 over 2 pi I right? And the Dirichlet series f of s makes sense for real part of s, let's say, bigger than 1. Now, here's where the power of complex analysis comes in. Supposing f of s admits an analytic continuation to a larger region, then I can now replace this contour. So I can first start by truncating this thing. So there's a truncated version of the Heron formula which you have to use. Let's say you truncate it at some height t minus t. And you can, let's say at s equals 1, it's got a simple pole. So you would kind of deform the contour and replace this. So thinking of this integral here from minus infinity to infinity as a limit from minus t to capital T, thinking of it like that, okay? We're replacing this vertical line integral by this kind of segment. And then we'll use Cauchy's theorem to say that this integral, or this vertical line here, is equal to the sum of these other 3 integrals plus, and you pick up the residue. So the main term is going to come out from the residue, and this is exactly the calculation that Riemann did. So without actually any of the theory, what he did was this: 2 pi I is equal to summation n less than x lambda of n, right? That's the formula. And then now you know that it has a simple pole s equals 1, so he picks up the residue there, so that's x. And then now he has to worry about what are the other singularities. Well, the singularities will be coming from the zeros of the zeta function, so he writes down x to the rho over rho for all the zeros. And then at s equals 0, there's the contribution that's going to come. So the fact is the Riemann analytically continued the zeta function of the entire complex plane. And that's how he was thinking about it. So he used that analytic continuation and realizes that I could go to the left as far as I want, which he does, okay? And he ends up getting, now maybe I got these numbers wrong, but more or less 1/2 log 1 minus 1 over x squared. So he just keeps going. There's a singularity s equals 0 that's coming from here. So he picks up that residue, and then he keeps going, and then there are trivial, so-called trivial zeros at negative even integers. And so when he adds up all those contributions, he ends up getting this, and he actually gets an explicit formula. Bang. So this is what's called the explicit formula. Riemann guessed it, and the person who proved it, I think, is von Mangold, the guy whose function we were talking about. So you need complex analysis to prove this, but he gives you an intimate connection between prime numbers, and these are the zeros of the zeta function in the critical region, so-called critical region. That means we showed there are no zeros to the right of 1, and one can show by what's called a functional equation that there are no zeros to the left of 1 except the trivial zeros. And once you have that, all the action is taking place between real part s equals 0 and real part s equals 1. And so those zeros give rise to that. So contour integration can actually show you this rigorously. But however, you need to know, you need to estimate these things on the horizontal contour and justify these limit processes. And for that, you need to study the zeta function in more detailed form. So this is the general method of contour integration. Using Perron's formula, using analytic properties, deforming the contour into the region where you pick up the singularities, and then estimating the function on these other lines, and then getting an error term. So that method of contour integration usually leads to very good error terms. So that's the method of contour integration. Okay. The second method is elementary methods. These are more difficult, of course, but sometimes not. These are just basically bare hands estimations and so on and so forth. And sometimes elementary methods may lead to better error terms, sometimes. For example, in the problem that I gave you as homework assignment that you asked about, counting number of square free numbers. So let's say we define mu squared of n to be 1 if n is square free. Well, why do I do that? Let's define mu of n. Let's define mu of n to be minus 1 to the power k if n is a product of distinct prime numbers and 0 otherwise. Okay, so this is a Mobius function. I think most of you probably have seen this already. Mobius function. So it's supported only on square free numbers. So if I square it, I can use that as the characteristic function for square free numbers. And now it's a multiplicative function. So I can write this as 1 plus 1 over p to the s, right? So that can be written as 1 minus 1 over p to the 2s over 1 minus 1 over p to the s, right? That's like so, right? So this is zeta s divided by zeta 2s. So in other words, if I look at the Dirichlet series associated with the characteristic function of the square free numbers, I have a nice expression for it in terms of the Riemann zeta. Oh, okay. Was it working before? Okay. Okay, so you have a simple pole at s equals 1, residue 1 over zeta 2, so automatically the Tauberian theorem tells you that this is asymptotic to because that's what it is, right? However, you're not going to get error terms this way. And if you want to get error terms, you can apply a more direct approach. The value of the Tauberian theorem is that it's extremely general. The elementary methods can exploit the special nature of the problem and get better error terms. This is a particular case in point. So here, small exercise. Okay, so I'll let you try and prove that. More or less it's there, but prove it, okay? So if that's the case, this is the characteristic function of the square free numbers, then q of x is just simply n less than x, d squared divides n mu d, right? I mean, that's what you have. Just plug it in, right? And now you do obviously the interchange of summation, d squared less than x, mu d. Inside you have to count n less than x, d squared divides n, 1. So this becomes d squared less than x, mu of d, x over d squared. Okay. And now you can see that I can remove the square brackets here, d squared less than x, mu of d, x over d squared plus O of 1. Okay. And now you get d squared less than x, mu d, well, x comes outside, mu d over d squared plus O of, well, the Mobius function is at most 1, and I've got at most root x summans. So it's O of root x. Okay. And this is a convergent series, so don't replace that by 1 plus little o of 1, then you'll get back your Tauberian business, and that's not a very good error term, right? So what you should do is you should say d squared less than x, mu d over d squared is the full series, d going from 1 to infinity, mu of d over d squared minus d squared bigger than x. In other words, d is bigger than root x, mu d over d squared, right? And now you can see that this is a constant, which we will write as 1 over zeta 2, right? And then this, you just put absolute values on the Mobius function, so it's summation 1 over d squared. It's a tail of a convergent series. The tail can be estimated by the integral dt over t squared, going from root x to infinity. And when you do that, it's all O of 1 over root x, right? Okay. And so I go back here and plug it in. And so what do you finally get? You get x times 1 over zeta 2 plus O of 1 over root x plus O of root x. And so this is x over zeta 2 plus O of root x. So you get this very good error term, square root of the main term, by an elementary method without any complex analysis. The complex analysis method gave you just the first term, but doesn't give you anything else. But that's a more powerful theorem, very general, too general that it's not going to give you error terms. But if you want to get error, so that's why you shouldn't downplay. I mean, there's nothing high or low about anything. This is an elementary method. It has its value, and it can be used to get good error terms. Okay? Now, there's one more comment, if I may take a little bit of time to discuss. That has to do with the question that Sumit asked last time about higher order poles. If you had more poles, could the Tauberian theorem be used to get asymptotic formulas? And the answer is yes. But you need a little trick to do that. And so I want to show that trick to you. Maybe do that now. So let me just say question. Oh, by the way, you may, since I did this example, let me just give you an exercise, homework problem, exercise. Derive a similar formula for the number of square full numbers by using elementary methods. Number of square full. So do the square full case. Remember last time I showed you how the Tauberian theorem can be used to give the main term, but now try and do it by elementary methods. You'll get a better error term actually. All right, that's a good exercise. Now, so the question is, can the Tauberian theorem handle higher order poles? Well, I'm going to say that it can, and you have to understand how to do it, though. That's all. So remember, there are these conditions about the application of the Tauberian theorem. So what did we prove so far? You give me a Dirichlet series, Bn over NVS. Okay. Suppose it has analytic continuation for real part s bigger than or equal to 1. Bigger than or equal to 1, with except for a simple pole at s equals 1, then summation Bn is asymptotic too. That's what we proved so far. Okay. But remember, the Bn has to be dominated by some An, which was, again, An was supposed to have non-negative things, and for which the Tauberian theorem is true. So you have to check the conditions of the Tauberian theorem. So supposing I have a situation where I have An over NVS, like so, and Ans, of course, are non-negative, and f of s extends analytically for real part s bigger than 1, except at s equals 1, where it has a double order pole. Double pole. Then what I do is I take f of x and I divide by the Riemann zeta function squared, so that I cancel the pole, and I get another Dirichlet series, G of S, call it. And so let's say that's Bn over MBS or something. Let me say it's Cn over MBS. Okay. And what you could do is you could check, let's see, f of s is equal to zeta s gs. And you can check. So you write this guy as summation Bn over MVS. G of S, remember, is analytic now for all over the place, like real part s bigger than or equal to 1. Zeta S now only has a pole at s equals 1. This guy is now analytic except for that pole, and it looks like this part of the thing is perfectly poised for the Tauberian theorem. So, but you just have to check the Bn satisfy the conditions that we want, that it's dominated by some An, such that not that An, but some other, that it satisfies. So you could try to apply the Tauberian theorem on this, and you would get summation Bn, n less than x, is asymptotic to some constant x. Or written differently, little o of x. Okay? But you're really after summation An. You're really after those guys. So what you do is you well, here's the method almost works, but not quite, and so I just want to explain this. So we know this. What we do know is An is summation d divides n bd. That's coming from this product. Zeta s times this guy can be translated An is equal to summation d divides n b sub d. Okay? So therefore, summation An, n less than x, summation An is now equal to summation bd x over d just by doing just putting that thing in. So writing this An here, and then interchanging summation, you get this. Okay? Now, because you know that summation Bn is a constant x plus little o of x, this is more or less saying that Bn is like a constant on average. So by partial summation, you can deduce from that summation Bn over n less than x, is equal to constant log x, same constant, plus little o of log x. So I'll leave that. Once you have this fact, you can deduce this fact by partial summation. I'll leave that to you. So that now it looks as if I take away the square brackets, and then this becomes d less than x, bd over d, plus o of summation bd, but summation bd is like o of x, so it's an o of x there. And then by partial summation, you have this. Get something like that. Okay, you could do that. The only problem, actually, there's no problem there. That's okay. So there's a small issue here, if you try to prove this by your partial summation trick, there's a small little trick there in this question, but I'm sure you'll figure it out. Okay, so that's basically how you could get. But notice that it only gives you x log x and doesn't give you the next term. It gives you a very crude error term. All right. And of course, you can continue this procedure for higher order poles. So the Tauberian theorem does give you information. So if the philosophy is that if you have a Dirichlet series with analytic continuation up to real part s bigger than or equal to 1, except at s equals 1, it's got a pole of order k, then summation an should be like constant x log x to the k minus 1. That's the bottom line of the thing. Okay, so that more or less covers what I wanted to say for this session, which is to be meant as an elementary introduction or introduction to analytic number theory. Now, Biswajoti has asked whether I'm willing to talk give a few more lectures on equidistribution, and I'm happy to do so. Here till Wednesday, so I could give 3 more lectures if people are willing to put up with this, and or at least are benefiting. I'm hoping you're benefiting from the lectures. So I could talk a little bit more about things like that. One of the things that it'll be useful is how much of this, the Tauberian theorem can be applied to zeta functions of number fields, and how one could use the Tauberian theorem to study distribution of solutions of congruences. These are all very interesting questions. Maybe I could talk about that and talk about equidistribution at the same time in a kind of a general sort of way, and that might help people in their study of number theory, if you are interested in it. So we can continue that next week, right? So at the same time, yeah, same time and same room, I guess, this room, okay. Same room, and we could do that perhaps next week. Okay.